Good morning, everybody. Last class we have discussed about the two-dimensional state of the stress and how we can analyze using the Mohr circle diagram to find out the principal stress, stresses and shear stresses as well. Now this time we will try to focus on the three-dimensional stress state. Uh, so far, we know that the tensor notation of the stress analysis can be represented like that: sigma xxx, sigma xy or yx, sigma zx, and sigma yy, sigma zz, like that. Now, this stress notation, tensor notation, we found out that there are 9 components of the stress in case of three-dimensional state, and all out of that there are 3 normal stresses and 6 are the shear stress components. A typical we represent the state of the stress assuming that the element, specifically for 3D, some cubic element, and we are showing that different stress component along x, y and z direction, like that. Along y direction, that is sigma yy, that is acting along the direction y, so it is considered as a normal stress value. But on the same plane we define the shear stress sigma yx and sigma yz. So here we see that sigma x is also acting, which is along the direction x, similarly sigma zz also, and other components sigma zx, sigma zy, sigma xy, sigma xz, these are the shear stress components. Specifically, when one element is subjected to some kind of loading in arbitrary direction, then we can convert that component of the load in the one specific direction, maybe in along the direction x, along direction y, or along direction z. So sigma yy in this case is the Fy by Ay. So Ay is basically area which is normal to the direction axis y. Similarly, when we represent the sigma zy, this is basically shear stress, and the shear stress, what is the force acting along the direction y, divided by the area Az. That Az actually represents the area normal to the z axis. So this will produce the shear stress and this will produce the normal stress, and within that one element, this all the components of the stress is simply represented by this way, or by the term of stress tension, where the diagonal element represents the normal stresses and off diagonal elements actually represents the shear stresses, and following some sequence or following some order, so that we'll be able to understand how this order is following, to look into the notation of the different stress tensor or sign convention, like that. So sign convention, if we try to focus on this say two-dimensional case along the axis y and z, if we see the direction arrow which is along the direction x, this is represents the sigma x-axis, that is the normal stress which is greater than 0. But shear stress, when it is acting this direction or opposite side, it is in that direction, that shear stress actually here is the less than 0, that means negative. So since the shear stress tau xy, it is opposite to y, that means negative y direction, but right hand side positive, it is a positive side of the x axis. So this, because of the negative direction of the y, that it is tau xy actually in this case represents the negative shear stress value. Similarly, when we consider this component, this is opposite to the x axis, so out of x and y, one is the negative x axis, so because of that this component also represents the negative shear stress value. similar way we can define, but if you want to define the shear stress, positive shear stress value, then it should act in this direction. We should represent in this direction, that actually represents the shear stress which is positive in this case. So depending upon the orientation of the axis, and we can adopt the several sign convention to define different shear stress value or normal stress value, and we can show whether it is negative or whether it is positive values. Now if we consider the moment with respect to A, that in general with respect to A moment equal to 0 for this element, so in that case we can say that tau ij equal to tau ji, or we can say the sigma ij equal to sigma ji. That actually makes the stress tensor symmetric with respect to diagonal. So we will try to deal with all the stress analysis respectively the symmetric stress matrix or symmetric strain matrix will be using further. Now similar to the two-dimensional analysis, here it is also important to know the transformation of axis. Suppose the state of the stress is defined in one axis system, for example IJK system, and we like to transform the state of the stress in another orthogonal set of axes, say for example M and P. So in that case, sigma ij, the component of the stress, can be represented like this. So where L Im or L Jn actually the direction cosine, so all L Im specifically the direction cosine angles between I and M axis, and L Jn is the direction cosine between the J and N axis. So in general we can write the sigma ij equal to L Im L Jn sigma Mn. This is the general representation of the stress with respect to different axis system. So now if stress is represented in XYZ coordinate system and we like to transform onto the x dot, y dot and z dot coordinate system, so by using this notation we can say that x sigma x dot, that is the one normal stress component with the new transformed axis, and that we represent that is equal to one component is the L x dot x, L x dot x. So here L x dot x actually represent the direction cosines or angle of cosines between the axis x dot and x. Similarly, the sigma yx or sigma xy component, that can also be multiplied by the direction cosines L x dot y or L x dot x. Then this is the way we can transform the stress, or we can define the normal stress or shear stress component in another new axis system. Here we find out that the stress tensor having total 9 components. So here 3 plus 3 plus 3, so total 9 components can be transformed using the direction cosines, and if we know the direction cosines between the old axis and the new axis system, and there is a system, this is the systemic way to represent or to transform the different stress state with respect to the new defined axis as compared to the old axis. So similarly, the shear stress components can also be transformed to the another axis system. That means here is the x dot, y dot and z dot axis system by the similar way. Now we can further simplify this expression looking into the symmetric nature of the stress tension, where we follow the sigma ij equal to sigma ji. With this symmetric nature we can further modify this thing, that means sigma x dot, or we can say that sigma x dot or sigma x dot equal to that it exists. There are 3 normal stress components and others are the shear component, and this transformation is having only 6 components, and with this transformation we can define the stress state and the another set of axes. Similarly, when you try to represent the shear stress, So similarly, we can further simplify the expression by looking into the direction cosines and the stress state, different stress components values. We can define the shear stress value in the another new set of axis system. So this transformation of the stress from one axis system to the another axis system, using this simple formula, we can find out this thing. Now we can verify whether these transformation equations are in right direction or not. Just last class also we have discussed that suppose theoretically we can estimate that in a two-dimensional system there is a initially the axis system is x and y. We have defined the forces Fy is acting on that Fy and along the x direction, that is Fx. Now we try to define one set of plane whose normal y dot is at an angle theta with respect to y axis. So with respect to the y axis there is the angle theta, and that y dot actually represents the normal to this highlighted plane. So from here we can find out that new normal stress value sigma y dot, or transform normal stress value with sigma y dot with respect to the sigma y which was defined in the x y coordinate system. Here we find out that sigma y dot equal to simply Fy dot by Ay dot, and Fy dot is the component of the force with respect to the Fy, that is Fy cos theta, and divided by Ay. So now Ay is the Ay by cos theta. So by putting this we can find out that sigma y dot equal to sigma y cos square theta. So by knowing that, here we see this is the cos square theta. So it is the multiplication of the, we can say that direction cosines, two directions cosines. If it is L and M with respect to different axes or with respect to the same axis, then it becomes the square. Similarly, shear stress on the new transform axis system can be defined the similar way, similar fashion. You can find out the sigma y cos theta sin theta. So if I define the direction cosines L and sin theta direction cosines M, so it is corresponding to the L M sigma y. So this is the way, that's a physical verification of these things, how the transformation of axis helps to define the stress state and another set of the axis system. So but if we try to use the formula what we have derived to find out these things, so sigma y dot, actually the new stress value at the new transform axis of y dot, then we can find out the direction cosine square into sigma y from here direction cosines L with respect to y and y dot, because they are making angle theta, that actually cos square theta comes into the picture. So here it becomes the sigma y cos square theta, which is very much similar to the what we physically verified by looking into the orientation of the plane. Similar way, the shear stress can also be calculated with the new transform axis, the two different direction cosines, and we can find out that it becomes again the two direction cosines cos theta and sin theta. So it should be, I think, x dot y and y dot y. So it is not the same direction cosines. These are the two different direction cosines, different values of the direction cosine, cos theta and sin theta. So if we, this is L x dot y and sorry L y dot y, and this is L x dot y. So these are the way we can simply transform the stress state which was defined in the one set of axis system with the another set of axis system. So this is significant to further analyze the principal stresses to find out the principal stresses on a specific stress state. Now if you look into one example for that transformation of the axis, we see that the example, we define the problem in such a way that a cubic crystal is subjected to the stress state sigma x equal to 15 kilopascal. For example, sigma y equal to 0 and sigma z equal to 7.5 kilopascal. So these are the stress state, normal stress state defined at the x, y, z axis system, but there is no shear stress acting on that. So we can simply say that tau yz equal to tau zx equal to tau xy equal to 0. Now the x-axis, y-axis and z-axis are also defined, x 1 0 0, y 0 1 0 and z equal to 0 0 1. Actually this x, y and z axis represents the axis of a cubic crystal. If you look in, it represents the cubic crystal. So we can define, this is x-axis, so 1 0 0 direction. So we can define, this is y-axis 0 1 0 and this is z-axis 0 0 1. So within the unit cell, we can define the direction as corresponding to x, corresponding to y and corresponding to z. So once we define z's, now we need to find out what is the shear stress on the 111 bar 101 bar slip system. So here we can see that 110 111 bar actually define the plane. So that plane, for example, these are the plane where the slip will occur, that is corresponding to 111 plane. Now 101 bar slips, that represents the direction. For example, this is the direction D, this is corresponding to 101 direction. So first we define the plane, and within that plane we define the direction at which direction the slip phenomena will occur. Now how to tackle this problem? So we can use our concept of the transform to the axis system to solve this problem. But here first we define that two different planes. First we define the plane, that 111, and we can define one direction n. So this n direction is basically the same index, but it is because with this index, same index, it is defined the normal to the plane. So here n is defined like this, 111 part. Direction D actually represents the slip will occur due to the shear loading. So D here represents the 101. Now we have explicitly defined the x-axis, y-axis and z-axis, but here we need to find out what is the shear stress. Shear stress is acting along the direction D, or specifically when you try to find out the shear stress tau in D, that actually define the one specific stress state system. D actually define the direction, which direction the stress is acting, and that is over the plane ND. Now we can find out the several direction cosine, say for example L and X, to find out the tau and D. L and X, L dx, L and Z, L dz, these are the components are required. So to find out basically the direction cosine between the axis N and X and corresponding to N and Z, or between D and X or D and Z. So it's a straightforward, because we have defined the N and D, and X is already defined 1 0 0 axis, Z is defined 0 0 1. So from this N, D, X and Z system, we can straightforward find out the direction cosines. So basically the dot product between these two vector, if we represent as in terms of vector N into X, so we can find out the L and X like this. If the Miller indexes is HKL, then we can find out n into x. So 1 multiplied by 1 plus 1 plus 1 0 0 plus 1 minus 1 0 0 and root over of 1 1 1 square, that means 3, and root over of 1 0 0 means 1. So that comes 1 by root 3. So that is correct. So similar fashion we can find out what is LDX, what is LNZ, and what is LDZ. Now tau ND actually represents, since the components here, if we see that sigma y equal to 0 and all the shear component equal to 0. So if we see the transformation of the axis system, we go back to that shear stress can also be calculated. There exist 1 2 3 4 5 6 components, but out of the 6 components, sigma 0, all are 0, yz 0, xy equal to 0. So during the using the formula of the transformation of one axis system to another, we are getting only 2 components. So that similar transformation formula, we use it, and we are getting the tau ND is corresponding to this formula, which is having non-zero elements sigma xx and sigma zz, and corresponding, it is multiplied by the corresponding direction cosine. So that direction cosine we can directly find out, and by putting here we can find out the value, and we can find out here the total stress value is equal to 9.186. So this is the way to track that this kind of problem, where the stress state is given one axis system, but we need to find out the specific stress state in the some other axis system, and in this case we can directly use the transformation of the axis formula for the stress, and we can find out we can solve the problem, or we can tackle this kind of problem. So few important things to point out specific to this problem. First one is that when it is given the slip system, we can define the slip system with respect to one. First we need to define the one specific plane, which plane the slip will occur, and second thing is that which direction slip will occur. So first, this indicates, actually clearly indicates, that this is the representation of the plane, and the second part, this actually represents the direction. But when you try to draw the normal direction with respect to one specific plane, that index will be the same. So this is corresponding to direction, and if one bar is the plane, so normal to that plane, that is defined by the 1 1 minus 1, the same. So this way we can tackle the problem also. Now we can go back to the, if there is a 3-dimensional stress state, then how we can find out the principal stresses. Like two-dimensional cases, we have already discussed that there must exist some principal stresses, in the sense the maximum minimum stresses value, when there doesn't exist any shear stress. But in 3-dimensional stress, we can find out the principal stress in a very straightforward way. First we need to suppose the stress state is defined with the matrix A, and x is the variable here in this case. Now we can define the characteristic equation such that Ax equal to lambda x. So the same state variable, but we are multiplying some constant term lambda. Further rearranging this equation in such a way we can find out this equation. So there must exist some principal stresses when the determination of this term is equal to 0. So other ways, the similar way we can find out if sigma is the stress state and n is the variable here, and we can find out the characteristic equation equal to 0. So this actually brings the determinant of this equation. So basically it is actually determinant of this equation equal to 0, since this cannot be, the variable state cannot be 0. So when you do this manipulation to find out the principal stresses, then finally we will be getting the one cubic equation like this. So the roots of the equation actually represents the principal stresses. So equation has the real root only when sigma is the symmetric in nature. So there exist 3 real roots in this case, and we can consider the roots of this equation as a principal stress value. So let us see how we can do the further analysis. So the values of the lambda 1, lambda 2, lambda 3, that is the roots of the cubic equation, represent the 3 principal stresses, and the 3 principal stresses often designated like at sigma 1, sigma 2 and sigma 3. The equation is independent of the orientation of the coordinate system. So here actually we are using the concept of the orientation of the coordinate system, and we are oriented the coordinate system in such a way that along that orientation the principal stresses actually exist with that specific orientation. So once we find out the principal stresses value sigma 1, sigma 2 and sigma 3, then we need to find out the principal direction n1, n2 and n3 using eigenvector problems. We are not going into details how to find out the this thing, the principal direction, but we can highlight these things that 3 orthogonal planes exist where there is no shear stresses. Sometimes we use the rotation matrix to change the components from an arbitrary coordinate system to principal coordinate system, and then rotation matrix is defined like this. So n1, n2, n3, m1, m2, m3, p1, p2, p3, these 3 actually define some orthogonal axis systems, and using this rotation matrix we can define the direction of the principal stresses. But for example, we can find out the other points that principal stresses or principal direction can also be found out considering the rotation matrix with respect to the principal coordinate system of the following tensor. So suppose this is stress is defined in this way 1 2 3 2 2 4 3 4 3. So here the 2 and 2, here also 3 3 4 and here 4. That means it represents the symmetric matrix. So first, to find out the principal stresses corresponding to the stress tensor, we need to formulate the cubic equation first. So here actually I1, I2 and I3 is it's called the stress invariance. So that we'll see that how this invariance can be represented in terms of the different stress components. So once the cubic equation is formed from the basic matrix of stresses, then this cubic equation can also be solved. First root can also be found out by Newton-Raphson method. Then when we can find out the first root, then another 2 roots actually forms the quadratic equation, and from directly solving that quadratic equation we can find out the other 2 roots also. So then after finding out all the roots of the equation or maybe principal stresses from one specific stress tensor, then we need to solve the eigenvector problem to find out the principal stress directions. But in this case it is easy to follow that to find out the rotation matrix, and it indicates the change of the components, this rotation matrix, from an arbitrary coordinate system to principal coordinate system. That means this is the arbitrary coordinate system to principal coordinate system. We can directly use the concept of the rotation matrix and to find out the direction. But this is beyond of the scope now. Now in terms of the stress invariance, we can represent the principal stresses, or we can modify the actual equations. So first, when you try to find out the principal stresses, that actually physically represent the set of axis system which is having no shear stress. So the normal stresses sigma 1, sigma 2 and sigma 3 actually called the principal stresses value. These are the roots of the cubic equation here. So the stress invariance I1, I2 and I3 can be represented like this. So here I1 equal to sigma xx plus sigma yy plus sigma zz. So here I2 equal to in terms of sigma yz zx and sigma xx y and zz. So I3 also represented like that. But remember that I3 is represented as the determinant of the sigma ij. So actually here sigma ij is equal to the what was the defined along the x, y, z coordinate system. So that is sigma x is sigma y and sigma z, and accordingly we can put the other components, and that is the representation of sigma y. So determinant of that actually it represents the third invariant, and second invariant we can follow directly the component of the stress value on the x, y, z coordinate system. Now this invariant can also be represented in terms of the principal stresses value. So the first invariant is the simply summation of the three principal stress value, and second invariant also in terms of the three principal stress value, and third invariant is just simply the multiplication of these three principal strains. So this expression is the more simply expression to remember. I think it's a more simplified form in terms of the principal stresses, but these expressions are also little bit more number of terms are also involved here. But this expression is the with respect to the original stress matrix, but this expression is the when we find out the principal stresses or principal stress axis. So it is that with respect to that it is defined. So we can say that 1, 2 and 3, this axis system the stress invariants are represented, and here the original xyz in terms of the xyz coordinate system the invariant system invariants are represented here. Now octahedral stress, one of the main component, or maybe this is more useful specifically when we try to analyze the continuum plasticity. So in this case octahedral stress is more significant, but the basic idea what is the octahedral stress here. The octahedral plane equally inclined, so for example point P equally inclined to all three directions with respect to the principal axis. So with reference to the principal axis, if it is equally inclined to all three directions, that plane actually defines the octahedral plane. So 8 such in a three-dimensional coordinate system if we consider, then 8 such plane exist, and each plane is called the octahedral plane. Now what is the normal stress on the octahedral plane? That is defined the 1/3 of first invariant. So 1/3 of first invariant is the simply 1/3 of three principal stresses, or you can say sometimes it's a simply average stresses or mean stress. Similarly, octahedral shear stress is in terms of invariant is like that I1 and I2. So here we can find out in terms of the principal stresses, these are the expression of the octahedral on the octahedral plane, the what is the shear stress value. Now these are the all in terms of the principal stresses, but similarly we can actual stress tensor in terms of the xyz coordinate system, we can represent the octahedral stress, that is the normal stress, and this is the shear stress value in terms of the x, y and z. Now look into some problem that we need to show the tangential component of the stress vector on the octahedral plane. That means tangential component on the octahedral plane means the shear component here is equal to 2/3 of J2 dot, where J2 dot is the second invariant of the deviatoric stress tensor. So here if we see that stress invariant is represented in terms of J2. So sometimes we can use the in terms of I2 also, and sometimes we use the stress invariant in terms of J also as well. So where J2 dot is equal to the second invariant of the deviatoric stress component. I will come on later the part what is the deviatoric stress component. but in each stress state can be decomposed into two parts. One is the hydrostatic component, another is the deviatoric stress component. So here dot actually represents the deviatoric stress component. So if we look into that, what is the second invariant in case of octahedral stress state? The second invariant are represented like that, simply negative of this principal stresses, that means sigma 1, sigma 2, sigma 2, sigma 3 and sigma 3, sigma 1. This is the representatives of the second invariant. So similar thing we will try to follow here. Sigma 1, sigma 2, sigma 1, sigma 3 and sigma 2, sigma 3, but D actually represents the specifically, it's the only deviatoric stress component. So and negative sign also given. So if we further manipulate this deviatoric stress component, if we put the expression of the deviatoric stress component, here we can find out this expression comes is like this: 1/6 of that sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So this is the expression of the second second invariant of the deviatoric stress tensor. Now what is the shear stress of the octahedral plane? That is that we have already derived this thing, and in terms of the x, y and z axis, that is the component of the octahedral shear stress. Now which is equal to the 2/9 the first invariant and the 2/9 second invariant. And then we can find out 2/3 of the second invariant. We can find out that we have already defined here, and 2/3 of the second invariant is also since this is the deviatory part and this is the deviatory, 2/3 of second invariant is this is equal to the tau octahedral stress. So here we can find out the tau octahedral stress is 2/3 of second invariant, this thing. So we use this formula J1, J2 and J3, that means all the three stress invariant. Now we look into another example to make it clear how we can find out the different principal stresses here. So for example, if we define the stress state one specific point, the sigma 1 1, sigma 2 2, sigma 3 3, 1 2 2 1, sigma 1 3, sigma 3 1 and sigma 2 3, sigma 3 2, all are given. Now we need to find out the principal stresses. Now what is the state of the stress? The state of the stress is defined like that. We putting the simply component, following some notation here. Here if you see the nature of the stress tensor, that it is symmetric, because here the shear component 1 2 2 1 equal to same, and 1 3 3 1 is same, and 2 3 3 2 is the same. So we define that as the stress state. Now if you see that this multiplier 2, if we make it is a common for all the components here, we can represent from here to here, keeping the 2 as a multiplier component here. So here 2 multiplication, so it's very careful to use this one. Now we need to find out the characteristics equation based on this stress tensor, so that we can follow in the similar way what we have discussed, that sigma, that all the diagonal component, the constant term, so deviation, and minus lambda, here minus lambda, and first one is the 3 minus lambda, and keeping the other component same. This is the equation. So now we put the determinant of this equation, that ultimately it is coming like this. So this is the cubic equation is formed here. Now direct investigate with the cubic equation, we can easily find out that lambda 1 equal to 1, lambda 2 equal to minus 2 and lambda 3 equal to 4. These are the three roots of this equation, but these roots of the equation of the stress tensor here, which is exclude the multiplying factor 2. So here actually principal stresses, when you try to find out the 4 is the one root, but we multiply the multiplying factor 2 here, similarly sigma 2 and similarly for the sigma 3, then we have find out the actual principal stresses here. So here maximum values of the principal stress is 8 and minimum is -4 and middle one is 2. Now we need to find out the normal and shear stress upon a plane whose normal is defined by the direction cosines. So we need to find out the normal stress and the shear stress component when the direction cosine is given. Now this plane with respect to the principal stress axis. So with respect to the principal stress axis, this direction cosines actually indicates the it's the octahedral plane. So on that plane we need to find out what is the normal stress, what is the shear stress value. So within the octahedral plane, this is the expression of the normal stress value, that is the average value, and we can find out that actual with respect to the 1, 2, 3 axis, it's a 2 megapascal. So that actually we can find out, this is the from the matrix here. So we use this plus this diagonal, the original matrix is 2 megapascal. But same thing can also be calculated by looking into the principal stress values, sigma 1 plus sigma 2 plus sigma 3. We can find out the same values. Now octahedral shear stress we use in terms of the principal stresses here, and you can put it here. We can find out the 4.9 megapascal. So these are the way we can find out the different stress state in the octahedral plane, and we can find out the principal stresses for the actual stress state. Now, as we already mentioned, that is a stress state can be decomposed into two components. One is the hydrostatic component, another is the deviatoric component. And for two-dimensional cases, the hydrostatic components of the stress actually cause the volume changes and not in plastic deformation. So hydrostatic component actually changes the volume without change of the shape, but may not be involved in the plastic deformation. But other way, the yield stress is not dependent on this hydrostatic component, but fracture stress actually strongly affected by the hydrostatic state of the stress. So hydrostatic stress is the average of the two normal stresses. So all these phenomena actually very much followed in case of metallic materials. Now suppose this is the stress state, sigma xx, sigma tau yy, tau xy and tau yx, and this is the two-dimensional stress on the xy axis system. Now hydrostatic stress component is the simply average of the two normal stress component. Now if is this stress state we can divide into two components. One is the hydrostatic part, another is the deviatory component. In hydrostatic part, we assume this is the hydrostatic stress component is, for example, sigma m. So only hydrostatic components are there, and another is the deviatory components are there and making the balance. So here if we find out sigma x, sigma y is this towards the hydrostatic component, and here is the deviatory component, all the four. So if you see graphically, if we try to represent, this is the initial stress state. We can define into two parts. One is the hydrostatic component. Here we see it is subject to only the equal amount of the stresses in the x and y both direction. But here the stress is different. The two normal stresses are different, but it is at the same time it is subjected to some amount of the shear stress. So this is corresponding to the deviatory stress component. So any stress state can be divided into these two components to make it the simplify the calculation or the individual effect of the hydrostatic stress or deviatory stress component for the further analysis or different plasticity theory. Similarly, in case of three-dimensional state, we can decompose the general stress state into two components, one is the hydrostatic stress, another is the deviatory stress component. So hydrostatic component is sometimes we say that is a pressure, defined as a pressure. So that is simply average of this thing, three normal stresses, and which is equal to the 1/3 of the first stress invariant. And now if we see, that is the sigma is the consist of the hydrostatic part, another is the deviatoric stress component. But the existence of the sigma p, so exists when you try to separate out the hydrostatic component, that does not alter the principal direction. So principal stress directions remains the same. It is independent of the amount of the hydrostatic stress values, but it does not contribute to the shear component. So that we have already discussed that in pure hydrostatic is only the normal stress component, but there is absent of the shear stress component. But the deviatory, both normal component as well as the shear component are there. Now by looking into the hydrostatic stress state, or when you try to divide the deviatory stress component and hydrostatic stress component from a general state of the stress, then by using the deviatory stress component we can find out the principal stresses almost in similar way. Now if we separate out only the deviatory component and if we find out the characteristic equation based on the deviatory component, we can find out this equation. But if we see that on this deviatory component, we can find out there are two stress invariant, although it is a cubic equation, but two stress invariant I2 and I3 is there, because I1 first stress invariant becomes 0 in this case. Then from this cubic equation can also be straightforward, can be solved by following, suppose lambda is the root of the equation, then we can find out directly, you can say that lambda I equal to 2 times of second deviatory invariant, third to the power half and cos alpha I. So alpha 1 and alpha 2, alpha 3 are also defined here, but when you try to find out the alpha 1, this formulation can also be used for further analysis if alpha 1 lies between 0 to pi by 3. If it is out of this range, then we cannot use this formula to find out the roots. In that case, from the conventional way, we need to find out the roots of the equation. Now, what should be the stress invariant when we consider only the deviatory stress component? So, if you see the deviatory stress component, if we sigma express the three principal stresses of the deviatory component, it becomes 0. Then second invariant of the deviatory component, it becomes in terms of the principal stresses is like this, and third invariant also like that. So see, we follow the similar formula to even for the deviatory stress component to find out the different invariant. And finally, these are the all expression of the deviatory stress component in terms of the principal stresses. Now, we have discussed the different types of three-dimensional stress state and how we can find out the principal stresses, but there are several comments need to address here based on the three-dimensional stress state, and where the three principal stresses are not equal, assume that things. So there may be the different possibilities that first is the three unequal principal stresses may exist in the actual case or in practically. When thus such situation exists, so sigma 1, sigma 2 and sigma 3 not equal to with each other, then we can say this is the triaxial state of the stress. Second case is that when two out of the three principal stresses are equal, for example sigma 2 equal to sigma 3 but that is not equal to sigma 1, then we can say the cylindrical state of the stress. Third case is three principal stress are equal. In that stress state, we can say that hydrostatic state or spherical state of the stress. So hydrostatic stress state that we have already discussed. Now in certain cases, the one of the three principal stresses is 0. For example, sigma 3 equal to 0. Then we can say the biaxial or two-dimensional state of the stress. Finally, 2 out of 3 stresses is 0. So only one stress is the principal stress is the non-zero. Then we can say the uniaxial state of the stress. So these are the different type of the stress state we practically apply or arise during the analysis of a stress with the actual problem. Now we come back to the what is the different type of stress state exist in case of cubic crystal structure. Maybe we can start with the stress state on the unit cubic and observe that the orientation of the cube is changed by rotation in the 3D, or we can take the view that we may look into the inclined plane with direction cosines L, M and N. So that direction cosines L is defined cos alpha. This alpha is the angle between one specific direction and with respect to that direction, basically the diagonal direction, and what is the angle alpha. And similarly cos beta, direction cosines M, cos gamma, direction cosines N. So stress state can be explained simply by observation in the cubic structure, or can be look into that analyzing, knowing the different direction cosines, and we can further analyze these things. So let us physically investigate what are the different stress state actually exist on in the cubic structure. So here is the most important, because plastic deformation actually happens by the slip process at the atomic level. So within the crystal structure, or the cubic crystal structure, it is more significant or important to know what is the maximum or what is the stress of the shear stress within the unit cell. So let us first under the different loading condition, let us look into the uniaxial tension. So that means when it is subjected to some uniaxial tension, what may be the stress state. If we say that this is the unit cell or unit cubic and it is subjected to a uniaxial tensile load, and it will produce a stress sigma 1, and that is the only principal stress is acting along this direction sigma 1. Then we can find out that two different planes such exist. It is highlighted here. So one plane is this, another plane is that, in the type of 0 KL. On that plane, that shear stress becomes 0. Now if we investigate some other planes, what is the state of the shear stress there? If we look into that another plane, this is the plane and this is the another plane. So all this plane actually defined with as a reference the coordinate system x, y, z. We can find out that if we apply the one principal stresses on this face or along this direction, those principal stresses is basically acting along x direction. Then this with respect to this direction, the plane highlighted here and another plane where there exists the maximum shear stress tau 2, where it is half of the normal stress value. Similarly, other orientation of the plane also sigma 2, but here this is sigma 2 equal to 0. And if it is subjected to sigma 1, only uniaxial stress, then here also tau 3, that means here also maximum stress can be produced sigma 1 by 2, that different planes, this and that planes, that is also highlighted. And here the plane where it is subject to the maximum shear stress. So all these planes can also be defined in terms of the Miller indices. Similarly, planes of the maximum shear stress or no shear stress, when it is subjected to biaxial hydrostatic tension. So if you look into when it is biaxial tension, say sigma 1 here, and here it is this axis, the another principal stress exists sigma 2, but here sigma 1 equal to sigma 2. So with this situation, the maximum shear stress actually produce the sigma 2 by 2, or maybe I can say that sigma by 2, where sigma 1 equal to sigma 2 equal to sigma for example. Then this maximum shear stress exists on two corresponding planes, it is highlighted here. Similarly, another two plane, that is also sigma by 2 shear stress, two plane, that is also exists when it is biaxial stress, and this will actually maximum shear stress. But some other planes, there exists no shear stress. So that no shear stress value is the simply Miller indices is the type of HK0, that type of planes within the unit cell that is subjected to no shear stress. But if we overall investigate these things, then when it is subject to sigma 1, both the equal biaxial stress state, or both side x and y axis having the similar amount of the stress, then we can find out the lines. This plane feels no, there are several planes exist not having the any shear stress, no shear stress, but some other planes it is subjected to amount of the maximum shear stress value. But when yielding can be take place, so slip will initiate due to the planes inclined in the third dimension which fell shear stress. Although it is explained that there is a certain plane exists, there is no shear stress, not subjected to the shear stress, but yielding will, because this is the completely subjected to the state of the shear biaxial state, but yielding may occur if there exists some shear stresses in the third direction. Similarly, you can investigate in the case of triaxial hydrostatic tension. So in this case, the sigma 1 equal to sigma 2 equal to sigma 3, all three axes the stresses are equal, and then it is typically subjected to the triaxial but hydrostatic stress state. So no plane feels any shear stress in this case, that is the case of hydrostatic tension. So shear stress will be 0 with this stress state. This is another case. For example, pull push, normal stresses, that means tensile stress, and another side is the compressive stress. With these situations, specific plane it is subjected to shear stress, but that's equal to minus. So here the two state of the stress, but they are equal in magnitude, but the direction is different. One is the tensile and the another is the compressive. So in this case, the maximum shear stress will be the sigma by 2, and another cases we can find out the maximum stress is the sigma by 2. One cases is the shear stress is negative, another cases we can positive according to the convention. So the planes are defined here also. So all this plane feel shear stress, which is the magnitude of the half of the normal stress value. But in certain planes also exist within the unit cell. Here it is marked this way. So that planes is actually subjected to the maximum shear stresses twice that of the other, with as compared to the other stresses. Okay, so twice sigma by sigma 1 by 2. So that means this is the twice of the what is subjected in this case, tau 1 and tau 2. Tau 3 is basically 2 times of the shear stress as compared to the other stress. So these are the typical stress exist with the application of the different load within the cubic crystal structure. Now we'll shift to the next topic, that is called three-dimensional strain, and specifically focus on the small strain. So like stress tensor, we can find out the strain tensor in the similar way with the designation with respect to the axis x, y and z. But during the deformation, actually it is subjected to translation, rotation as well as the distortion. Specifically this figure indicates for the two-dimensional body. But small strain actually defined by excluding the effect of the translation and rotation. So small strain consider the only the distortion. So if we look into this picture, it's a displacement with the x and y axis, along x and y axis is represent the displacement u and v. Now suppose A, B, C, D was the initial position, and after application of the load, this is the final position A dot, B dot, C dot and D dot. So this final position and the initial position, if we compare, the final position actually subjected to both translation, rotation as well as distortion. Now how you can find out the distortion in this case in terms of the displacement u and v here. Suppose AD dx AB equal to that elements AB equal to D1. Now when you try to estimate the strain along x-axis, so epsilon xx is the what is the A dot D dot. minus initial value AD with respect to the original AD. So this is the expression of the strain in this case. Now the displacement of points in continuum may result from the rigid body translation, rotation and deformation, that is in actual case, but when you try to focus on the small strain tensor, then we can estimate the difference this A dot D dot AD in terms of the dou u by dou x with respect to dx. This is the initial, that is the final, and what was the initial was the A. So corresponding to that, that is the difference and with respect to the initial length. So dou u by dou x actually represents the strain here. Similarly, epsilon y, that means y direction, the normal strain can be defined dou v by dou y. So partial, this represents the partial derivatives of displacement v with respect to x or y. Now when you try to represent the strain as shear strain, basically in terms of the angular form, so in the small distortion case, the shear strain can be defined, can be approximated that the simply the angular the angle. So here the shear strain actually represents this part, the total angular form here. So the angle between AD and A dot D dot, angle between AD and A dot D dot, and AB and A dot B dot, that is AB and A dot B dot, that angle and this angle actually represents the shear strain. So from here you can find out that basically we try to find out the angle. If angle is theta, we try to find out the if angle is theta, we try to find out the tan theta here, and that tan theta is by dx, and we can find out dou v by dou x, and another component is the dou v by dou y. So total angular deformation we can say that consider the shear strain, that is the dou v by dou x plus dou v by dou y, and due to the symmetric nature we can find out gamma x yx equal to gamma xy. So these are the elementary shear strain we can find out. And if we see that if we see the graphical representation of the shear, that if you see that with the application of the load with small element, two-dimensional element, this is the pure shear happens without any rotation. So simply the initial position was the dotted line. With the application of the load, it takes that shape. The solid line actually takes the final shape, that is subjected to pure shear without any rotation. Now with the deformed shape, if we simply rotate, then it takes this shape, that is called the simple shear. So that simple shear, this angular form actually consists of these two, both part is there. So here we can already define the normal strain is like that, but the shear strain is this component and that component, which comes from two different parts, and finally the represents the shear strain is this by the two component. Now Moll strain tensor can be represented the similar way what we did for the stress tensor, and these are the typical expression of the shear strain component. Mathematically, the shear strain epsilon ij is the half of the engineering shear strain epsilon ij is the half of the engineering shear strain. So that's why we have written the epsilon x, y or yx, whatever, with this half of the shear strain, and we can represent these are the components of the shear strain. Now transformation of the axis, what we did in case of the stress analysis part is the similar to the it is also in this case it is also similar to the translation for the stress analysis part. We can use simple formula transformation of the axis like that: epsilon ij equal to L Im L J N and epsilon mn. So we can find out that, so L represents actually direction cosines, and here we are trying to find out the transformation with respect to x, y, z, that is corresponding to x dot, y dot and z dot. That axis system, what is the state of the strain? Similar way, using the direction cosines, we can find the 9 components, and that again 9 components can also be considered as the 6 component within the symmetric nature of the strain component as well. Similarly, shear strain also can also be calculated from the 9 component to convert to the 6 components with the similar to the stress analysis part. So now transformation of the axis in the strain, specifically here the analysis is focused on the small strain, but the large strain, some comments on the large strain tensor. The large strains are not tensor and cannot be transformed from one axis system to the another simply by a tensor transformation. What we did, the angles between the material directions are altered by deformation. That is also true because this large strain tensor we cannot transform using the simple transformation, because in this case the angles between the material direction actually altered by the deformation. But with small strain, change of angles can be neglected, and we can use this transformation of the axis from one axis system to the another axis system when we assuming there is a small strain tensor exists. Now we look into one example to make the clarification or application of this transformation from one axis to another axis to apply in the problem itself. So similar kind of problem we have discussed, but this is the further extension of that. For example, consider an aluminium single crystal that has been stretched in tension applied parallel to the x-axis 100 by 250 kilopascal. So sigma x is basically 250 kilopascal. In compression parallel to y-axis by 50 kilopascal. So this is the y-axis and it is subject to the 50 kilopascal, but it's a compression and with 0 kilopascal phi z. So sigma z equal to 0. Now slip system, so I think sigma y can be like that, minus of 50 kilopascal. Now with the slip occurs on this plane 1 1 1 and 1 bar 1 and 0 this direction. So for example, we define this slip plane, this corresponding to that plane 1 1 1 and direction d on the which slip direction will occur 1 bar 1 0. Also assume that the strains are small. So in this case, if the crystals were strained epsilon x is 0.01, then what may be the strain along y direction and the angle between the tensile axis and 1 bar 0 we need to find out. So first we define this plane, that plane, and the normal direction to this plane n is basically 1 1 1 the index and d 1 1 0. So that z axis also defined. So all axis system is defined here, but the different direction also defined here. Now we use the transformation of the axis from one axis to the another axis. We can find out. So here d epsilon x is the consist of the n d and d epsilon y, the two direction cosines, and the strain on the with respect to n and t. Now here we can find out the direction cosines similar way, lnx and ldx, similarly no ny and ldf, all direction cosines we can find out. Now we can find out the ratio of the strain, it is -1. So d epsilon y by d epsilon x almost its ratio is the same. So similarly with this stress state, we can simply find out the range of the strain is same as the range of the strain. But with this analysis we can find out that this problem actually we are not using the data of the applied stress, because we assume that strain, normal strain along x-axis is equal to the two direction cosines, and with respect to the shear strain with respect to the ND. So similarly with respect to y is the amount, the same amount of the shear strain along the direction D on the ND plane. So that's why it's the direction cosines are same. So it is the range of the strain with in y axis also the same. Now angle between the x and D can be considered as the phi. So that means x and D, x equal to 1, 0, 0, and D have already I defined. Angle between the tensile axis and 1, 1, 0. So x axis is the tensile axis here, and 1, 1 bar 0. So 1, 1 bar 0. If we put between this thing, we can find out the angle between 1 by root 2. That means phi equal to 45 degrees. So these are the typical problem. So simply using the knowledge of the transformation of the axis, we can apply this problem to solve or to analyze the stress state in specifically happening in the within the crystals itself, single crystals, or maybe we can use it in the polycrystalline to solve the strain or plastic deformation or slip mechanism in polycrystalline material as well. So hopefully it was understandable, the analysis of the strain, and actually purpose was to analyze all these strains, how to apply the knowledge of the three-dimensional or two-dimensional stress strain specific to this subject. That means in case of different crystal structure or the plastic behavior of the different crystals in this case. So hope you enjoyed this analysis of the stress state in a very simplified way in case of two-dimensional as well as the three-dimensional. So next time I will shift to the next module that is basically the different theory of the plasticity that we used very specific to the continuum scale or normal materials, but not very specific to the individual crystals as well. So thank you very much for your kind attention.